Hi everyone, welcome to Machine Learning Week 5. Well, it turns out I'm still stuck at the airport, so I thought I'd type this introduction for you. Today we're going to be going over the basics of the bias variance trade-off, one of the key results in the machine learning theory. When we have a machine learner that learns very specific patterns in the data set that won't generalize to the test set, we'll say it's overfitting. It won't capture the regularities that we expect to see in the test set. Shall we take a look and get started? So before we get started on week 5, it's good to go recap what we've learned in our lecture on week 4 on linear and logistic regression. In both cases, regression means that we're getting some real valued output. But in the case of logistic regression, we're using that real valued output as the probability of a binary event. And we saw in both cases we can write down a cost function, which we're going to denote as J for Jacobian, which is going to be a function of the actual theta values we ultimately choose after executing our learning algorithm. In the case of linear regression, we're going to use squared error, which is just a signal minus the actual value, and then taking that for each example and squaring it. And for logistic regression, we're trying to make sure that we match the actual sign values by taking this signal and multiplying it against the actual classification. And in the case where there's a mismatch, for example, one is positive and one is negative, we're going to end up with an exponentially large term, which is going to penalize that misclassification. In both cases, we saw that we could use gradient descent to come up with a solution. This works by taking steps in the opposite direction of the gradient of the cost function. We saw in the case of linear regression that there's also a closed form solution called the normal equation. And that gradient descent has a particular speed up, that one of stochastic gradient descent, where we do iterations over individual points rather than the entire batch. We saw that in the limit, the expected value of such a pointwise direction is going to be actually equivalent to the same as the gradient of the cost function itself. This is a great form of optimization because it means that the training time is no longer dependent on the size of the training dataset. Now it's time to check out what we're going to learn this week. As we've introduced, we'll be looking at the bias variance trade-off. We're going to understand why overfitting occurs as a result of the bias variance trade-off and the role of model complexity and the sample dataset that causes it. We're going to also show how the effect of a noisy target contributes another source of noise, and be clear about the role of data resources towards model selection, which is very much related to the idea of overfitting.